Okay, well, thank you to the organizers for inviting me. And my title of my talk changed halfway through the meeting, but this is what I had intended to talk about. And I took the liberty of changing the, well, I guess this doesn't show up if I do this online.
It does not show up online.
Right,
yeah.
okay, so I'll have to use this, hopefully that shows up. There we go. Okay, I took the liberty of changing the title of the meeting by throwing an extra colon in. So, all right, my collaborators on what I'm going to talk about are Jazir Ahmed, who did work with us on single spin asymmetries. He was a student at the University of Manitoba and has now got a faculty position in Pakistan. And Craig McRae is a graduate student who did some work on global form factor analysis, and my longtime collaborator, Wally Melnichuk. So here we go. All right, so an outline, I'll talk about single spin asymmetries, target normal, which we heard a little bit about from Jose Goiti in the first day, and beam normal spin asymmetry cases. I'm going to talk a little bit about the current status of two-photon exchange calculations for elastic EP scattering cross sections. Some of the issues that arise in extracting proton electric and magnetic form factors using two-photon exchange. So the famous GE over GM ratio, issues of nonlinearity and epsilon that keep cropping up, and some comments about form factor parameterizations and things that, from our perspective, make life difficult and which should be avoided. So the spirit of this talk, I'm not going to do polished results. I'm going to show you, in some cases, things that problems we've encountered. So I'm going to not try and hide the problems we've encountered, particularly with the beam normal single spin asymmetry. So I'd be interested in your input on some of those things. So what we do is rooted in the dispersive method, if you like. We deal with on-shell intermediate states, intermediate electron and hadronic states. So the blob here represents it could be resonant states, it could be the elastic nucleon state, it could be non-resonant background, which is not in our calculation. And the idea is that the imaginary part of the amplitude that gets folded in with the one photon exchange amplitude, the imaginary part can be written as a sum over nucleon states with two virtual photons being exchanged. Typically, there are form factors at the hadronic vertices, and one does a sum over those states. And typically, since those states are continuous, there's an integral over the virtuality of the hadronic state, which I'll call W. So the imaginary part is determined by unitarity. This approach uses only on-shell form factors, or equivalently helicity amplitudes, that are directly fitted to data. And the real part is then determined by a dispersion relation from the imaginary part. So we've used the class model, which has a number of intermediate resonant states below 2 GeV. They're listed here. So the delta and a number of others. The important ones tend to be the N1520, N1535. And so the class collaboration has produced helicity amplitudes from electroproduction data. And typically it has a bright Wigner line shape associated with it. So I've just taken, this is just from their most recent paper. And if you can't see the scale, that's not important. Really what I wanted to show is some indication of the quality of the data that goes into our calculation. So the top row is the delta, which of course is very well known. And then the N1440, you can see the width of the green curves is some indication of the uncertainty. and then the N1520 in the bottom. So there are, of course, others, but these are the helicity amplitudes that go into our calculation, and we'll make use of the uncertainty bands as well to give some idea of the uncertainty in our calculation. Theory calculations should always come with an uncertainty band, which is, of course, not the uncertainty of the theory itself, but the uncertainty of the input into the theory. The uncertainty of the theory itself is a big, maybe you consider that a systematic error for theorists, but that's one we typically don't want to talk about. Okay, so two-photon exchange using dispersion relations. It's convenient to express things in terms of generalized form factors, which are associated with matrix elements. And so for two-photon exchange, there are matrix elements which look very similar to the F1 and F2 form factors that crop up in one-photon exchange, not by accident, but they're functions of q squared, and nu is the basically the energy. Think of it as an energy. And then there's an induced axial coupling, which arises because of the two-photon exchange effect. So the delta, the enhancement of the one-photon exchange comes from the real part of those generalized form factors. It's a ratio of that to the one-photon exchange reduced cross-section. So it's sensitive to the real part, which means we have to do the dispersion calculation. So these are the dispersion relations for those three. The F1 and F2 are odd in nu, and the effective axial one is even. But what's important and what makes this non-trivial is that these integrals extend into the unphysical region down to zero energy, which, if you like, corresponds to a cosine of theta being less than -1, or a negative virtuality of epsilon. So it's we have to extend things into the unphysical region, and I'll discuss how we do that. But before I talk about the real part of the two-photon exchange, I'm going to talk about the single spin asymmetries, which are direct measurements of the imaginary part. So, and this is all in the physical region because you produce real particles. So there are two types. There's the target normal spin asymmetry, which Jose talked about on Monday. And so it's denoted A sub n. You can think of it as a fraction or a percentage from a target polarized normal to the scattering plane. But what's important here is that this asymmetry uses the same three generalized form factors that crop up in the real part. Now, this is the imaginary part here, but it's the same three generalized form factors. And so if you do a measurement of A sub n, you're really probing the same contributions to two-photon exchange that crop up in the cross-section case. Well, it's the imaginary part, but we're sensitive to the dispersion integral of that. On the other hand, the beam normal spin asymmetry has an additional dependence on spin flip form factors. So there are two other, which I've denoted F4 prime and F5 prime. I think we can thank Misha Gorstein for this notation. But in any case, I am not going to talk about particular generalized form factors, but it's a different combination. And so a measurement of B sub n is telling us something different about two-photon exchange than what one might directly learn from the target asymmetry. All right, so let me start with the target normal spin asymmetry. There's very little data for the target normal single spin asymmetry. This is at relatively low energies, 2.2 GeV. And what I've shown here are the contributions from different intermediate states. So the delta is the biggest contributor. And then you can see the uncertainty band is highlighted in pink or light red. It's centered around what I call the complex mass case. Now, I'll mention what I mean by these different things, but we can have a zero width delta, or we can have one with a bright Wigner width. And then the third one, which is a teaser at the moment, is to use the complex mass, the pole mass, for the delta resonance. But for the target normal spin asymmetry, it doesn't really make much difference what you use. Remember, we're integrating over W. So it turns out, in particular, because the target normal spin asymmetry doesn't have any quasi-singularities, that it doesn't really matter whether you take a zero width resonance state or not. You tend to get very similar predictions. So you can see the delta, of course, is very well known. The other states contribute less, but are considerably more uncertainty. So you note the different scales on the left-hand side of these contributions. And then if we go to higher energies, these are the same resonances at 6.6 GeV. Then I'll just switch back and forth. So you see the delta is somewhat bigger. The other ones are bigger as well. And so the relative uncertainties increase as you move to higher energies and higher angles. All right, so if we add them all up and get a total, and as I said, I don't have any data to compare with, so I can pretty much say whatever I want. So this is 2.2 GeV, but it gives you an idea of how the uncertainty increases as you increase the angle. So this is at low energies. That's the kind of thing we might expect. And as you move to higher energies, the relative uncertainty increases because of the contribution of the higher resonances. All right, but it's the scale is, of course, in percent. So you're looking at about a 1% effect here. All right, so the things to note, this is free of kinematic enhancements at thresholds. Jose talked a little bit about a threshold effect, where his below threshold, he had no delta, and then it suddenly appeared. And that happens when the Mandelstam S is equal to W squared. But there's no quasi-singularity there, and there's no significant dependence on the width, is the other thing to note. All right, so that's the target normal, which is relatively uninteresting, in part because there's no data. But things get really interesting when we talk about the beam normal single spin asymmetry. So I've taken this picture from a talk almost 20 years ago by Barbara Pasquini. She did some work with van der Hagen in 2004, and Andre also did some work on this with Marenkov in 2004. So the beam normal spin asymmetry is proportional to the electron mass. So it's a 10 to the minus 6 effect, right? It has certain quasi-singularities, if I want to call it that. So when either one of the photons becomes soft, there's what they call a quasi-virtual Compton scattering. But the nasty one, depending on your perspective, one person's nasty singularity is another person's opportunity. But the nasty one is what they call a quasi-real Compton scattering, which is where both photons are soft and the electron, the intermediate electron, has essentially zero momentum. Now that happens when W is, if you include the electron mass, W is root S minus the electron mass. So it's basically at a threshold. Now, why is that a problem? Well, as I said, some people think this is an opportunity for an enhancement of the beam normal single spin asymmetry. But unlike the target normal single spin asymmetry, the quasi-singularity is not, it's there, all right? And when S is approaching W squared, things blow up, which doesn't happen for the target case. So I would characterize this as a quasi-singular behavior at the threshold. It's analogous to real Compton scattering. And so what I've shown on the left is a calculation for the delta in a particular case of beam energy of 1.15 GeV, which is the Q weak, actually, Q weak energy. So S is 1.72 GeV, well above the delta resonance mass, which is 1.2 GeV. So this is the line shape, or this is the function which gets integrated over W. And you can see, of course, there's a nice peak here, which is the delta peak. And there's a bright Wigner shape. And I folded that in with the kinematic factors. And you can see this nasty little surprise when you get close to threshold, the 1.72 GeV, it starts to blow up. It actually doesn't go to infinity, but it gets very large. Now, I find that disturbing. And I find it disturbing because the bright Wigner, we're a long way from the resonance here. And the bright Wigner line shape is really only an approximation. It works well near resonance, but far away from resonance, there's no reason to believe that it really works well. So this behavior is going to be highly model dependent, which I find unsatisfactory. Right? So we thought about other ways to think about this. And one of the alternatives we explored is this idea of using, for the delta, the complex pole mass. And this has cropped up in the literature. I'm not going to go too much into it. But for the delta propagator, you would replace the mass by the complex mass. And it's actually a gauge invariant way of doing things. And so we said, well, let's try it. Let's see what happens. And so this is, I plotted the B sub n as a function of energy now for angles, two fixed angles, forward angle 35 degrees and a backward angle of 135 degrees. So the blue, which at threshold is about 0.34 GeV for the delta. So this is, of course, the bright Wigner shape. You get a big enhancement. The yellow curve here is what you get with the complex mass, which doesn't show any such behavior. So I'm quite happy with that. And of course, here's, this is some data which is taken between 30 and 40 degrees at low energies. So we overshoot the data, but everybody does. So this is, well, I'm not sure it's right or wrong. I'd be interested to hear people's feedback about using a complex mass in the propagator, but definitely it's better behaved than the bright Wigner width. And it's even more pronounced if you go to backward angles. So the B sub n increases at backward angles. So the complex mass term is about 3 times larger, but the bright Wigner one is considerably more than that.
Complex mass, you mean that you have a fixed point, not actually depends in the imaginary point.
It means in the propagator, in the delta propagator, we take the mass is not 1.232, it's whatever it is, 1.1 with a width which is 100 MeV.
Okay, thank you.
All right, so let's compare with some other calculations. This is the additional data points which were published by Go et al. In 2020 from the Q-week experiment. So these are some older calculations you probably can't read, but the dotted line here is the nucleon, I believe, which is like our nucleon piece here. And then I've just plotted the delta here, which is the most important in this region, but there's some other calculations by the hashed one is Pasquini and Vanderhagen, and the green one is Misha Gorstein. Gorstein's one looks very similar to our delta one here, but all of them overshoot the data at these energies. It was nice of Misha and Barbara to put uncertainties on their calculation. This would have one as well, but I was lazy. All right, so if we look at the whole range of theta, this is the Q-week data point. The uncertainty is much smaller than the triangle that's there. I'll zoom on it in a second, but you can see this would be a zero width delta. This is the bright Wigner shape, which agrees well at low angles. And then the dashed one, the dashed red with the uncertainty band is using the complex mass. So very different predictions at backward angles. If we zoom in on the low theta values, then these are, this plot was taken from the Go paper. So here's the Q-week data point with a very small uncertainty. And then there are 3 theoretical predictions. There's Misha's right here, which looks very similar to, this is our calculation. So the Gorstein calculation is very similar to ours. But this is a very severe test. Of course, these uncertainties are small, and it's a very severe test of the theory, the theoretical results. But at small angles, of course, things, if I go back here, you can see the scale is at backward angles, things get much more magnified. All right, so I'll show some other data. This is the from the A4 experiment. All of these data come from the parity violating asymmetry measurements because they need to know contamination of their parity violating signal from the beam normal spin asymmetry, which is why they measure it. So this is the contribution from different resonances, the delta, the N1520 and N1535 are the significant contributors to this energy. And you can see again some differences between the treatment of the width. And so here I've shown for a range of energies. So this is the total now. So 0.855 GeV, 1.5 GeV, and 3 GeV. And something interesting emerges from this. The calculations tend to overshoot the data at low energies. And so here at 0.855, we overshoot the data just as it was, just as I showed earlier. At 1.5, it nicely goes through the data. And then at 3 GeV, we tend to undershoot the data. So there's maybe some other interesting things going on. What's not in our model, we don't have anything with a non-resonant background. So this is strictly the resonant pieces. But anyway, there's some interesting physics going on that is not in the models if the measurements are to be believed. So I'll leave that out as a teaser. Okay, so I'm done with the single spin asymmetry. So let's talk about the real part of the two-photon exchange, because it's cropped up a few times this week. So just a few technical details, and I don't want to go into it in too much detail. But if we think about this loop diagram and the interference of that with the one-photon exchange, then you can express the result as a four-dimensional integral over the imaginary part of the product of electronic and hadronic tensor. These are the photon propagators. And the imaginary part reduces to an integral like this. It's an integral over the angles of the intermediate electron. We have a numerator, which is basically polynomials in the photon virtuality, photon momenta, Q1 squared and Q2 squared. G1 and G2 in this picture are generic form factors or hadronic or helicity amplitudes, which are functions of Q squared. and then the 2-photon propagators for the imaginary part. Okay, so we would like to be able to use arbitrary form factors. Experimentalists don't typically parameterize their helicity amplitudes in terms of things that theorists like dipoles or monopoles. So we'd like to move beyond that, and that's fine because this integral can be done. It's a straightforward numerical quadrature, and you can easily do this integral in the physical region. So these G's are transition form factors that have poles in the complex Q-squared plane. I'll say why I want to talk about the complex plane. So as I mentioned, we have to evaluate this integral in the unphysical region, and that's where things get interesting. And so there was a very nice paper by Sasha and van der Hagen in 2015, which used the idea of using contour integration to evaluate these integrals. You can even do that in the physical region. This is a common problem in analysis for undergraduate students to evaluate these kind of integrals. You convert it to a contour integral and sum up the residue at the poles, and that solves the problem. But we're doing it also in the unphysical region. So they wrote a very nice paper on doing this for the elastic case using dipole form factors, I believe, and then summed the residue at the pole and got a nice result. When we looked at this, I looked at this with Wally Melnichuk. What we did was, first of all, extend it so that we could do inelastic states. But we wanted to use arbitrary form factors. And so the whole thing, rather than summing residue at the poles, you can just do a numerical contour integral. So you convert everything into the complex plane and do a numerical contour integral, which is just a line integral. And that allows you to use general functional forms for the transition form factors. The only caveat is that you have to be able to analytically continue your form factor or helicity amplitude into the time-like region, which is the unphysical region. All right, so let me just make a few comments about parameterization of form factors. It doesn't seem to be a problem for the inelastic cases because the class people use nice, well-defined form factors for what they're doing, but it does seem to be a problem for the elastic case. So this falls into also how global analyses are done using particular form factor parameterizations. So I'm going to call it the good, the bad, and the ugly. So there are good parameterizations, which are ones that have, it should be no poles in the space-like region. You're allowed to have poles in the time-like region, no poles in the space-like region. I'll correct that in the final version. So polynomials, exponentials, dipoles, and monopoles all have poles in the time-like region. Those are easily handled. There are what I would call bad but tolerable, which are things like ratios of polynomials, which is a favorite way of fitting form factors. The trouble is, of course, when you fit these things, you're fitting them along the positive real line, right? For space-like Q squared, space-like real Q squared. So of course, there's usually no poles there because there's no poles in the data. But these things can have poles elsewhere in the complex plane. And in particular, we don't care about poles in the time-like region, but we do care about poles in the space-like region. And so if this parameterization has a pole in the space-like region, which is the right half of this plane, then we run into trouble if you can visualize it this way. This is a plot of something centered at Q squared over 2 and radius Q squared over 2. So you produce this blob. Everything is fine as long as there's no poles within the blob. So if there are poles somewhere, then eventually at some Q squared, you're going to start to run into a problem. You're going to encounter the pole. It's not an insurmountable obstacle, but it just requires some special handling. which makes it a nuisance more than anything else. But you can do it. The ugly ones are things that have branch cuts, spline functions that can't be analytically continued to the complex plane, and so on. And there's my pet peeve, if you like, are square root functions. So people will, for example, fit the form factor squared because that's what comes into the cross section. They'll fit that to, as Gremlin and Nikolenko did, to a polynomial in Q squared. The reason they did this was because they wanted to do a linear fit rather than a nonlinear fit. But even the GMP12 paper that just came out in March uses this form for the magnetic form factor, but for the electric, they took the ratio of electric to magnetic as a polynomial in Q squared. So of course this is like a square root function. It has other bizarre behavior too. I don't know why, but I don't know why the ratio of GE to GM should be a quadratic. It implies things are going to run away at high Q squared. So, and it can be negative. So I don't know the significance of a positive definite quantity that can become negative, but anyway. All right, so let's get to the gist of it. So this is the two-photon exchange corrections as a percentage plotted as a function of epsilon for the full model. So this has all of the elastic piece, the delta, all the other resonances in there, ranging from 0.2 GeV. If I went down to 0, you'd get the Feshbach effect, but 0.2 all the way up to 5 GeV squared, which we kind of set as 5 GeV squared. Beyond that, we kind of get a little hesitant about a hadronic model. It's better to maybe describe it in terms of other degrees of freedom. So the interesting thing to note is that these results, they're fairly smooth. They're sort of linear over a wide range of epsilon, but they tail off from linear towards the endpoints. So models that take unitarity forces us to go to 0 at epsilon goes to 1, which is the high energy limit. But there are models that take, that rather than calculate the two-photon exchange, they take a model and say, well, it's linear in epsilon because the Rosenbluth cross-section is linear in epsilon. And you probably overestimate the slope then, because the slope is certainly not as large as you would get if I made a straight line from here back. All right. So I was hoping with Craig that we would have a global analysis to show you, but I don't. So I'm going to show you a poor man's version of extracting form factors, which of course should be done properly in a global analysis. All right, so the experiments I'm going to focus on are the Walker and Andevajis, which are the old SLAC data. I had some stuff in there from the Super Rosenbluth results, but the Super Rosenbluth has published no details about their radiative corrections, and so don't really know even what to do with it. So I'm not going to say anything much. So we're going to look in the region 1 GeV to 8 GeV squared, which is the polarization transfer. This is the data above Q squared of 1, and the green band is a fit. So let me, all right, so these are the details. Gremlin and Nikolenko, despite the poor choice of form factors, did a nice job of redoing the analysis of the radiative corrections on the old experiments. And the GMP12 further did a little bit further work using Gremlin and Nikolenko as a base. So they made a number of improvements to the standard radiative corrections. And so we'd like to put the two-photon exchange corrections on at the same level to add it to these corrections. And so We've again used exponentiation with these corrections. Basically, we took what either GMP12 or Blunden and Nikolenko did and added the 2-photon exchange corrections from here. All right. All right, so what is the effect? One of the things that's always pointed out is that the Rosenbluth plot assumes, or if it's 1-photon exchange, everything is linear in epsilon. So if you add 2-photon exchange, does that destroy the linearity of the data? And the answer seems to be no, it doesn't. So this is the original data. Well, it's not actually the original data, it's the data after Blunden and Nikolenko improved it, but without the 2-photon exchange. And this is the result with the 2-photon exchange corrections. And so in this definition, the intercept here would be the magnetic form factor squared. It's divided also by the dipole form factor. So just to set the scale. So this is at 2 squared of 4 from the Andevas data. There's really no evidence for any nonlinearity there. So rather than a global fit, if I wanted to just extract the form factors from the slope and the intercept, then you can do that. This is at the other q squareds of those data. And again, there's really no evidence across the range of q squared for nonlinearity. This is at 5 GV squared. Clearly, the slope is consistent with 0. And this is the Walker data, the same thing. So this is the 2-photon exchange corrected data. And really, there's no evidence for any nonlinearity there. So what is the effect on the form factor extraction? So this is the GE over GM band. This is the original data, which is GE over GM is consistent with 1. This is the extractions from the slopes that I just showed you, with the uncertainties, of course, increase considerably. In particular, the end one here, the uncertainty is enormous. So this is the Walker in blue and the Andevas in red with the 2-photon exchange corrections. So this is GE over GM. And if we wanted to look at GE and GM separately, then on the left is GM. So there's some tension here between Walker and Andevas, but GE over GM would be insensitive to any normalization differences. Whereas if there was a systematic difference in normalization between Walker and Andevas, it would show up here. But these are the direct extractions of the form factors, magnetic form factor from the Andevas data. And I cheated here for the electric, because the uncertainty bars are so huge, you can't say anything about it. But what I did, I said for the GE, let's just use the GM values and multiply by the GE over GM from the polarization transfer ratio. And there the Walker and Andevas line up fairly well. So this is the direct extractions, and this for fun is 2 form factor parameterizations from a number of years ago, which tried to account for 2-photon exchange as known at the time. So this is the Kelly in yellow here, the Kelly parameterization. And the blue one is John Arrington and Wally Melnichuk and John Chong. This is how, now of course this is 20 years old. So, but with the new improvements, this is how they stack up. So in summary, the beam normal single spin asymmetry is interesting and challenging. How to handle the quasi-singular behavior is an interesting issue if we want to handle it at all. One should really try and do something about the non-resonant background, a way to improve that. And Sasha has done something using the MAID analysis. And then just a comment, the results of the E plus E minus experiments are by no means definitive. problems remain at high epsilon, which are not resolved within this framework. But my gut feeling is that a proper inclusion of the two-photon exchange will likely resolve the polarization transfer and LT differences at high Q squared. So we would definitely like to see E plus E minus measurements at high Q squared and low epsilon. So, thank you.
Thank you very much.